21, starting the section on absolute value in this video on our semester review. So it says, describe the effects of the parent function when it has been transformed to the function below. So a couple of things we have to recall. We have to remember our transformation rules. So we have function notation. Remember, you have your A multiplied in front, outside the absolute value bars. And then you have X inside and a possible minus H, which would be inside, and then a plus K on the outside. So you need to remember what A, H, and K do. So A, I'm just going to go ahead and highlight. We'll look here. So in this one, it's negative. This one, it's 2. This one, it's 1/2. This one, it's -2. Okay, so the A value tells you the vertical stretch or compression. Now remember, if that A value is greater than 1, if it's bigger than 1, it's a vertical stretch. And if that A value is less than 1, technically between 0 and 1, because it's not going to be negative. Well, it could be negative, but that doesn't affect the stretch or compression is what I should say. So if it's between 0 and 1, so like a decimal or a fractional value, like 1/2 here, then it is a vertical compression. Now when it is negative, it is a reflection over the x-axis, so a vertical reflection. So normally the absolute value graph is the V that opens up like this. We did that when we talked about the parent functions. If you have a negative multiplied on the outside, it flips it over, and so it looks like this, like it's opening down. So that's a positive versus a negative A. So let's go ahead and list the transformations based on just the A's. So this one, it's an understood 1 for the number, so there's no stretch or compression. It is just a reflection over the x-axis. This one is a 2, so it is greater than 1, which means it's a vertical stretch. This one is 1/2, so it's between 0 and 1, meaning it's a vertical compression. And then this one is -2, so the negative tells us it's a reflection. And the 2 tells us it's a vertical stretch. Okay, so that's how A affects your graph. Right now we're focusing on absolute value, but that's how it affects it for all of your functions. All right, so then your H is subtracted on the inside. Now that could be a plus, but in the formula it's a minus. So if it shows up as a plus on the inside, like here, that means you're subtracting a negative, because minus a negative changes it to plus. Okay, in this one it is a minus, so that matches the equation. In this one it's a plus, so that means it must be a negative number for H. This one, there's nothing inside the absolute value bars with the H, so nothing to highlight from the pink. Now what H does, H, let's see if I can. Let's see if it would let me scroll, but it's not. Okay, so what H does is a horizontal shift. Okay, so that's a shift left or right. That's what we mean by a horizontal shift. I guess that looks confusing having the arrow pointing up, so let me just highlight. Okay, so H is a horizontal shift left or right. Now what that means is, because it's a minus in the equation, if it's minus a number, I'm going to redo my highlighting, so it's just the H itself. So if it is already a minus, that means the value there is your H. So here, H is an understood 0 because there's nothing there. Here, H is a -5, because that's what changed it to plus, is minus -5. Here, H is a +5, because the minus is already there from the formula. And here it would, so it's always the opposite of what's inside. Okay, so then looking at H, this one means there is no horizontal shift. A -5 tells me this is a shift left 5. Okay, so it's the opposite direction than you would think, because it says +5, that makes you want to think it's to the right, but it's the opposite, it's to the left, because H is actually negative. It's the opposite sign that you see in the equation. So here it's positive, so that is a shift right 5. Here it's -3, so that is a shift left 3. Okay, so when it had a plus, that was to the left. When it had a minus, that was to the right. Okay, so that's what you need to be sure that you're seeing there. I will highlight that. So no horizontal shift here, horizontal shift left 5, right 5, left 3. All right, and then last but not least, we have our K. So K is the value that's added or subtracted on the outside. Okay, so we can see that's 3 here. There's nothing here. Now this is -3 here and 5 here. So because in the formula it is a plus, it's exactly what it appears to be. We don't have to worry about opposite signs. Okay, so since this says +3 on the outside, we know K is 3. This has nothing added on the outside, so K is 0. Here has a -3, so K is -3. And here is +5, so K is 5. So K right here is a vertical shift. Okay, and that is up or down. That's what K tells us. It's our vertical shift up or down, and it's the direction that you think it would be. So since this was a +3, that means it is up 3. Since this is 0, this means there is no vertical shift. Since this is a -3, this means it's shifted down 3. And since this is +5, it's shifted up 5. So that's what the A, H, and K tell us for transformations. Okay. Let me right here, a -A is a reflection. Okay, let's move on to 25. So now these are asking us to solve the absolute value equations. So what you have to recall is to solve an absolute value equation, the very first step is to isolate the absolute value. Okay, the piece in the absolute value bars, get that by itself. Okay. In this case, that is this. I'll go ahead and highlight in all of them. This is the piece that I'm trying to get by itself to start. That's my step 1. Okay, so over here, I've got a 2 being multiplied and a plus 24 being added that I need to move. When you're solving or isolating a certain variable or part of the expression, you do the opposite order that we normally would for PEMDAS. So normally you PEMDAS is multiply, divide, and then add, subtract. But when we're working backward, you do it backward. So you do any adding or subtracting first. So this 24, the opposite operation is to subtract. We're going to move that first. Okay, you can draw the line to separate the left and right of the equal sign if you need to. So that gets rid of it on this side. Okay, so then over here I've got -8. Then you get rid of anything that's multiplied or divided. So this times 2, the opposite is going to be to divide by 2 to get rid of that. So now we have accomplished our first goal, which is to isolate the absolute value expression. Now you need to remember, once you have that isolated, there's 3 possibilities. Your absolute value equals a positive, it equals 0, or it equals a negative. Okay, so what that tells us, if our absolute value expression, once it's isolated, is equal to a negative, that means there is no solution. Because there is no way we could take the absolute value of something and get a negative. Absolute value is the distance from 0, and distance is never going to be negative. So in this case, because it's equal to a negative, we know there is no solution. Okay, now the other possibility, if it equals 0, that means there is only one solution. And I just take out what's in the absolute value, set it equal to 0, and solve. If it is equal to a positive number, that means there are 2 solutions. Okay, now when we talk about solutions, I know I talked about this in the other video talking about the quadratics. A solution is where the function crosses the x-axis. It's your x-intercepts. So if it's helpful, once you isolate the absolute value, we can put this in Desmos and get a visual of the graph, and then you can just look for where it crosses. There's a couple different ways to do that, so I'll review those in a second. Let's go ahead and solve number 26 algebraically. So we want to isolate the absolute value expression, so we're going to get rid of this divided by 2 with the opposite operation of multiplying by 2. Remember, what we do to one side, we do to the other. So that isolates our absolute value expression and leaves it equal to 10, which is a positive number. So I know there's going to be 2 solutions. Algebraically, what I do is I take what's inside, so that 3x minus 5, and I set it equal to positive 10, and I set it equal to negative 10. And I'm going to solve each of those. So now it becomes 2 separate problems. So here I would add 5 to both sides, and then divide out the 3. And I get x is 5 for one solution. I do the same operations over here, but it's to a negative 10, so it's going to come out slightly different. Okay, and I'm just going to leave that one as a fraction since it doesn't divide out evenly. So I have 2 solutions there. And then for 27, our goal is to isolate the absolute value expression, and we've actually already done that here. There's nothing to move away from it, from the outside of it. So it's set up as an equation, an expression that it's equal to, instead of just a number. But we're going to do the same thing we did here. We're going to take what's inside and set it equal to the positive version of this side, which is just 6x minus 7. And then we're going to set it equal to the negative version of that side. Now, if I was to take this and put a negative, don't forget I would have to make both terms negative. So it'd be equal to negative 6x, and then that would become plus 7. Okay, so I'm going to solve both of those separately. So here, I have x's on both sides, so I need to get the x's to the same side of the equal sign. It makes more sense to me to move the 2x because I know I'm subtracting it, and that will leave me with a positive over here. If I had moved the 6x, I would have to be dealing with a negative. It doesn't matter, you can do it that way. It's just my preference to leave it as a positive if I can. Okay, so I get rid of the x's on the left, and that becomes 4x minus 7. So I've gotten the x's to one side, now I need to move the constants to the other. So I'm going to move the 7 over here with opposite operation. And then I'm going to divide out the coefficient of 4. So that's one of my solutions. Okay, over here I'm going to do the same thing, except this time it's 6x is negative, so to move it I would be adding it, so I'm going to move it to the left because that'll give me a positive. So that becomes 8x minus 5 equals 7. And I'm going to add that 5 to the other side. Divide out the 8. That doesn't divide evenly, but I can reduce it because both of those are divisible by 4, which leaves me with 3/2. So those are my two solutions there. Now, with absolute value, you can always check with any function, you can always check your solutions by plugging it into the original function, and it should make it a true statement. So for instance, I should take this 5 from number 26 and plug it in up here. 5 times 3 is 15, minus 5 is 10. The absolute value of 10 is 10, divided by 2 is 5. Yep, it checks out. Okay, so you could kind of check it off as you check it. Okay, if I plugged in a negative 5/3 up here, the 3 and the third would cancel. I'd be left with just negative 5 minus 5 would be negative 10. The absolute value of negative 10 is 10. Divided by 2 is indeed 5. Yep, it checks out. Okay, and we could do the same thing on this side, but notice there's x in 2 places, so you would have to plug it into both to make sure you're checking that it's true. So 2 times 3 is 6. Plus 5 is 11. The absolute value of 11 is 11. So the left side comes out to 11. When I plug in a 3 over here, 6 times 3 is 18. 18 minus 7, also 11. So that one checks out. Okay, I could check 3/2. Again, the 2 times the half will cancel. I'll be left with just a 3. Plus 5 is 8. The absolute value of 8 is 8. So the left side comes out to 8. And then on the right, if I plug in 3/2, the 6 over 2 is 3. 3 times 3 is 9. And then 9 minus 7 is 2. So that one, that didn't come out, did it? Let me redo that. I'm going to show the work for that one. So if I'm plugging in 3/2, okay, so over here, 2 is reduced. That's 3 plus 5 is 8. The absolute value of 8 is 8. Over here, 6 over 2 is 3. 3 times 3 is 9. Minus 7 is 2. Those are not equal. So that is an extraneous solution. Okay, so that's why you always want to just double check your answers to make sure that they work. Now, in terms of Desmos, in terms of doing absolute value functions in Desmos, let's look at that. Here we go. Clear out what we were doing with the systems here. All right. I'll show you this first one and check it first. So we're going to do 2, and then the absolute value bars on the keyboard down here, right above the ABC. It's this absolute value of A, and then you can type what's inside. So x minus 14 plus 24 equals 16. So I can click on home and it recenters your graph. Okay, I don't see it, so I'm going to try zooming out. Well, how come I don't see it? Okay, I don't think Desmos is going to graph it when I have it set equal to a number. So I'm going to have to move that 16. I need to drop the equal sign and just have the expression, but I have to have it set equal to 0 to be able to do that. So I do have to subtract the 16 over. So if I subtract the 16 over to the left, so 24 minus 16, that's going to make that 8. Why is it still not? Oh, there it is. Oh, okay. I'm going to double check. Did that go away? Let's see. 6, oh, it's 24 equals 16. Yeah, it didn't graph when I did it that way. So yep, you just got to move everything to one side to set equal to 0 or equal to 0, equal to y, however you want to think of that. And then you can get the graph to show. But we can see here, this graph does not intersect the y, or excuse me, the x-axis. That's why there's no solution. Now your other option, actually, you can write the left side of the equation, so that was the plus 24, in one line, and the right side of the equation, so in this case 16, you would need to write it as y equals 16. You could write both as y equals, that doesn't matter. But okay, so if you do that, now you can visually see that these two do not intersect. There's not a solution, because the solution would be where they intersect. So no solution. So if I try that with 26 and put the left side, bx minus 5 divided by 2. So that's the left side of the equation. Then the right side is just that 5. We can see that these two intersect twice. We're looking for that x value. So we can see that happens at 5 and at negative 1.667, which is negative 5/3. And if you're unsure of that, you can type in negative 5/3 and see it as a decimal. Okay? So that confirms that the solutions we found work. So technically, could you do this without doing the algebraic work? Yeah, you can do this just in Desmos. You can put the left side in, the right side in, both set equal to y, and you're looking for the points of intersection, the x values where they intersect. Okay, so now if I try that for number 28, oh, it won't. Let me move this over to number, or 27, I should say. Okay, that's weird. Let me switch sides then. Okay, so for 27, we've got 2x plus 5 on the left, and on the right, we've got 6x minus 7. So we're looking for where these intersect. Now you'll notice those only intersect one time. Okay, so when we algebraically came up with two solutions and checked them, one was extraneous, it didn't work. So the point where those actually do intersect is where x is 3. Notice we got x is 3. Okay, so left side as y equals in Desmos, right side as y equals as Desmos, and look for the intersection. You can also work backward from your answer choices. Like I said, if you plug the answer choice in, it should make the equation true. If If it doesn't make the equation true, like this one, it's not your answer. So you can work backward from your answer choices. You can use Desmos graphing, or you can do the algebraic steps that we learned. Okay, and just remember, once you have that isolated absolute value expression, you can immediately tell how many solutions you should have. So sometimes you can narrow down your answer choices just knowing, hey, there should only be one solution. So I can mark out these two choices because they have two, or whatever. Okay, so it's good to know that as well. All right, I think that was it for the absolute value. Yeah, this gets into then polynomial operations, which is unit 5. I'll do that in a separate video. All right, so this video on absolute value is done. Check out the other videos. I show lots of those shortcuts. I'll just point it out real fast if you're still watching. Here's our canvas. You can see their videos are broken down by question number, and there's lots of shortcuts. Learn the shortcut in Desmos for 3x3 systems. Learn the shortcut in Desmos for solving quadratics. Okay, so giving you lots of little tips and tricks and shortcuts since there's so much material, a whole semester's worth of material. If you get the calculator, use it. All right.